Hello guys, it's been a while since my last video and I come back with a complete new topic, time complexity in C++. And let's go to our topic today because it is one of the most important aspects in competitive programming, and you must learn it from the fundamentals. Before going into today's sections, we have complexity calculations, common complexity and constraints, and constant factor. So there are three sections that we are going to go through today. Okay, let's get started. First, about complexity calculations. So as we know that we want a method to calculate how many operations to take to run each algorithm in terms of the input size n. And fortunately, this can be done relatively easily using big O notation, which is defined as expressing the worst case time complexity as a function of n as n gets large. So you can easily conclude that complexity is the upper bound for the number of steps an algorithm requires as a function of the input size. So in big O notation, we denote the complexity of a function as O Fn, where constant factors and lower order terms are generally omitted from Fn. So the next slide, I'm going to show you a few examples. So as you can see here, I initialize three A equal 11, 14, B for 14, and C 18. So we have three variables here, and I also initialize an integer d, the int type variable d, which is the sum of A, B, and C. So this code is considered to be O1 because it only executes a constant number of operations. Okay, so that's the time complexity of a constant number of operations. Now we come to the calculation of the time complexity calculation of for loop. So we have the for loop here and the while loop here. So I must say that input and output operations are also assumed to be O1. So the code inside our loop is O1. Therefore, the complexity of loops is the number of iterations that the loop runs. And here we run our iterations for n times. So as a result, the following code examples are both ON because we constantly run our time code for n times, as you can see here. As for other codes, we have the definition of constant factors and lower order terms. So in theoretically, if we run a for loop like this or like this, these are called constant factors and lower order terms. So in fact, they don't affect much about the time complexity calculation, because uh, approximately our complexity is still O(n). So we can assume that the complexity of these two examples of code are O(n). So we gonna find the complexity of multiple loops by multiplying together the complexities of each for loop. As you can see here, we have two for loops. The first one, the outer loop, runs with the complexity of O(n), and the inner one runs with O(m). So as the multiplication of the two complexities will give us the complexity of O(n) times m, which is the time complexity of this code. In this example, the outer loop runs O(n) iterations, and the inner loop runs anywhere between 1 and n iterations, which is a maximum of n. So since the big O notation calculates worst case time complexity, we treat the inner loop as a factor of n. So in this code, if we estimate the complexity, it should be O(n) squared. So I mistyped here a little bit. So, but as we ignore the constant factors and lower order terms, our exact complexity is n times n plus 1 divided by 2, because here is the explanation. So when you start at I equals 1, j goes from n to n, runs n times. When I starts at 2, j goes from 2 to n. So our code will run n minus times, and so on. We add all this together, which is the sum from 1 to n. We can easily calculate the time complexity. The exact one is O(n) times n plus 1 divided by 2. And if our algorithm contains multiple blocks, its time complexity is the worst time complexity out of any blocks. So here it is, so the exact complexity here is O(n) squared plus n plus this constant. But as we ignore the constant factors and lower order operations, the time complexity is still O(n) squared. And here, because neither of these loops is a lower order function, so our complexity is O(n) squared plus n. So these are a table that I cut from the user code guide. So it shows us complexity factors that come from some common algorithms and data structures. So as you can see here, O1, O log n, like the logarithm of n, and all this. And as long as we continue to develop our coding skills, we will soon learn the time complexities of all of these algorithms and data structures. So the last part, we come to constant factor. So we all know that constant factor is the actual number of basic operations an algorithm performs. So example, 3 plus 4 plus 5 or 3 plus 4 are both O1. So, but however, 3 plus 4 plus 5 is clearly slower because it performs more operations. So then we come to a conclude. Assuming that even though two algorithms both have O(n) squared complexity, one can be faster than the other due to a smaller constant factor. So we must pay attention to constant factor whether our code meets the time limit exceeded. So theoretically, our algorithm is correct, but we keep using unnecessary steps, and you using with a large constant factor, a data structure with a large constant factor, and you're iterating through more elements than you need, so it may make your algorithm fails to get all accepted with the competition test cases. So in summary, constant factors did affect real-world performance, even if our big O notations stay the same. Theoretically, they are ignored, but they do matter in practice. So constant factor is especially important when the time limits are tight, you are doing heavy nested loops, and you are choosing between data structures. So that's the end of our lesson today. I hope you can enjoy my lessons, and you can subscribe and like this video if you think it is useful, and the subscription will give you notifications about my newest videos. So take care. We will soon meet again.